Hello Year 11s. This is going to be a short video talking about energy. Energy is a concept that's behind the physics internal which you are currently working on. And you should know that if you want to gain a really good grade, you need to link your findings of your internal to physics theory. So here we go. What is actually energy? Energy can be defined as the potential to do work. And I'm talking about work in a physical sense here. It is measured in joules. That's a capital J, if you can't read that. And 1 joule worth of work, of energy, is actually not a heck of a lot. I can demonstrate to you. This is a bar of chocolate that has a mass of 100 grams. Okay? So the weight force that pulls it down to the ground is 1 Newton. If I'm lifting this bar of chocolate from the ground up to 1 meter, this bar of chocolate has just gained 1 joule worth of gravitational potential energy. I've done work. I moved the force of 1 Newton over 1 meter. That gives us 1 joule worth of energy. If I drop it, at the bottom it had 1 joule worth of kinetic energy, movement energy. By the way, if you look at the back of the bar of chocolate, here it'll tell me that this bar of chocolate actually has 2,200 kilojoules worth of chemical potential energy stored in it. That means there's 2,200,000 joules worth of energy stored in the chocolate bar. So I should be able to do that exercise 2.2 million times after I've eaten that chocolate. That's nonsense, because most of the energy we take in when we're eating goes to actually heating our body, keeping it at 37 degrees. But that comes later. So here goes the law of conservation of energy. It states that energy can't be created or destroyed. It can only be transferred from one form into another. So we can't actually make energy, and we are also not able to destroy it. So to explain that, you're trying to cycle over a hill. Now, if you're at the base, you have to do a lot of work to climb up that hill. You can only do that if you've had a good breakfast, if you've got stored chemical potential energy in your body. That allows you to do work, that allows you to move your mass and the mass of the bike against a distance, the height of the mountain, up that mountain. Once you're up there, you have gravitational potential energy now stored in you and your bike because you're on top of the hill. You won't have to do any pedaling anymore going down that hill, and your gravitational potential energy will be transferred into kinetic. So you will be picking up speed as you go down that hill. You won't have as much kinetic energy as you had gravitational potential here, because in real life some of the energy will be lost in the form of friction and air resistance. So we're losing some of that energy, and that goes into heat, heating up your tires and actually the atmosphere. So I can't destroy any energy. Let's see. Rather pathetic attempt of a roaring stag. Doesn't matter too much, you can't go hunting anyway at the moment. But where did that sound energy go that I just produced? Did I destroy it? Actually, I didn't. The sound waves were traveling and spreading out in this room, and sound waves are pressure waves within the air. So the particles of the air have been moved. They gained kinetic energy. They started vibrating. They actually were heating up. So all I did is the energy that came out of the end of my funny roaring horn is spread out and diluted within the room to the point that we won't be able to detect it anymore. But it did not get destroyed. So the law of conservation of energy is upheld. So a key type of energy you really need to be familiar with is gravitational potential energy. It can be calculated using this little equation here. EP equals mass in kg times gravity, that's 10, a constant of 10 here on Earth, times the height in meters, and we're talking the vertical height here. Okay? So what this tells me is that the more mass an object has, the greater its potential energy. The more height it has gained, the greater its energy. And I can demonstrate it. Here's a small light object with a laser nut. It has a small amount of gravitational potential energy, which will turn into a small amount of kinetic energy as I drop it. And I hardly feel it once it hits my foot. If I use a slightly bigger object, a walnut, that has a bit more gravitational potential, which will turn into a bit more kinetic energy, will turn into a little bit more ouch factor, but still quite bearable. Not sure why I'm doing this, but if I now use, in the interest of physics and science, a reasonable size rock, and I'm going to drop that with a fair bit of gravitational potential energy on my poor foot, that will turn into a fair bit of kinetic energy, and into a fair bit of ouch. So better don't do that at home. So the last form of energy I want to discuss in a bit of detail is kinetic energy, or in other words, movement energy. If an object is moving, it has kinetic energy, and kinetic energy can be calculated using this equation here. Ek equals 1/2 times the mass in kg times the velocity in meters per second squared. Now that squared here is crucial because it means that the energy goes up exponentially with velocity, not in a linear sense like with the mass. If you double the mass, you get twice the energy. But if you double the velocity, you will gain 4 times the energy. So I've quickly done that for you, working out if a car is traveling at 100 kilometers an hour, and let's assume that car has a mass of 1000 kg, 100 k an hour is 27.8 meters per second. If I square that, multiply by 1000, divided by half, I get 386,000 joules worth of kinetic energy for a car that travels 100. The same car traveling at 120, 1/2 times 1000 times now 33.3 meters per second squared, gives me 556,000 joules. So while the speed has gone up from 100 to 120, only 20%, the energy has gone up much, much more, because that's more than 200,000, just under 200,000 joules gained, which is a heck of a lot. And that's where that ad came from. The bigger the speed, the bigger the mass if you have an accident. So just going 20% over the speed limit causes you a lot more damage if you have an accident. Now let's start our demonstrations with a classic example of energy conversion, bow and arrow. So I've got Nina here with a bow and arrow, and I'm zooming in. Over there is our target. Coming back. Okay, now let's have a look how this works. In order to convert energy, first Nina has to do work by pulling the string back at the bow. And the bow gains elastic potential energy. Only on release will the elastic potential be turned into kinetic energy. Let's try that again. First we have to do work, pulling the string back, and then elastic potential gets released to kinetic energy. Okay. Pretty impressive, I would say. 2 good shots. So here is an example of a plant that's able to convert solar radiation, which is a form of energy, via photosynthesis to chemical potential energy within the fruit. And here's a device that converts chemical potential energy in the form of firewood into heat and a little bit of light energy. Alright, I hope you guys enjoyed this little video on energy. If you have any questions, feel free to just flick me an email. Otherwise, please look at the links I will have put on Google Classroom for you to check up on. So enjoy and keep safe.